Moving on to rational functions. I'm going to take some of that previous work we've done and tie it into some new things. So a rational function is a function of two polynomials. So think of a rational function as something that has variables in both numerator and denominator, or variables in the denominator only. Numerator only, we can rewrite in linear form. So something like x minus 3 over 5. That's really a linear function. We can rewrite it as 1/5 x minus 3/5. So to be considered rational, we need variables in at least the denominator. Oftentimes we get variables in both places. Another way to determine if a function is rational is, does it have a vertical asymptote? In other words, is it undefined somewhere? If the answer is yes, it's probably going to be rational. If it is defined everywhere, it's not rational. A rational function will have a place where it will be undefined, because a rational function will have a vertical asymptote somewhere. Here are some examples of rational functions. These are not examples you really need to write down because there are an infinite number of rational functions. Here are just some things to observe about them. Notice that every single one has a denominator with a variable, and also notice that some have variables in both. Like the f of x does not have a variable numerator, the others do. The f of x function is undefined at 0. The other functions, it's a little more complicated as to where they're undefined, but there are places that they are. So, another thing I want you to notice, this is something that's going to come up a little later on in our next video. I'll point it out for now. We have a term called degree. The degree of a polynomial is basically its highest exponent. So when I look at f of x, the denominator has a degree of 2. That's the highest power in any term. The degree of the numerator is 0 because there is no variable there. Looking at g of x, the degree of the numerator is 2, the degree of the denominator is 5. So the degree of the numerator is smaller. For h of x, their degrees are equal. They both have degree 3. For I of x, the degree of the numerator is larger. And we're going to come back to that concept in the next video. But for now, it's something to put in the back of our minds as being important for where we're going. And that is the idea of an asymptote. Asymptotes have several kind of sort of good definitions. The mathematical definition that's pretty common, though, is it's a line that is tangent to a curve at infinity. Tangent means touch. Back in geometry, you learned about tangent lines, lines that touch a circle at one and only one point. It's a line that does not go into the circle. It hits a point on the circle, but never goes inside the circle. Because a circle has constant curvature, that is possible. An asymptote is a line that's going to touch a curve at infinity. It's a fancy way of saying we will never get there because we can never get to infinity. But as we get closer and closer and closer, an asymptote gets closer and closer to the curve. Or the graph of a function gets closer and closer and closer to an asymptote, but it never gets there. Three types of asymptotes. One that you're familiar with is the vertical asymptote. This is where functions are undefined. And I've indicated them in these green dashes here. So notice this function gets closer and closer and closer, but it never gets there. It will never, ever, ever touch that. If it was possible to get to infinity, this curve would touch the asymptote. But because it's impossible to get to infinity, they will never meet. Same thing here. As this gets closer and closer and closer and closer to the asymptote, the distance between them gets smaller and smaller and smaller. So as x approaches this number, let's say this is -3, so negative 2.99999999999, we get really, really, really close to that asymptote. We'll never ever get there. Same thing here, same thing here. As x gets really, really close to this value, it'll approach that asymptote from two directions, but it will never get there. The function has to jump over the asymptote to continue its graph. Second kind of asymptote is a horizontal. These can be crossed several times. This one's crossed twice, but as x gets very, very large, the function will eventually approach it. Just like here, if x gets very, very negative, the function will eventually approach it and not cross it again. Think of a horizontal asymptote as kind of a limit, or it's sort of in the long run, we'll get really, really, really close to this number. In the short term, we can cross it. Think of some like interference, or some effect that makes things jump over it and jump back. But in the long run, as things stabilize, we will approach that value and never reach it. But we'll approach it. Same thing here. Last but not least is one you've probably never seen before, the slant asymptote. Think of this as a vertical. A slant is not crossed. It's like a vertical asymptote that's been tipped on its side or tilted a little bit. You often see these with parabolas. With hyperbolas that are not standard. So here I have a vertical, here I have a slant, and now we have this graph that has to deal with two asymptotes simultaneously. This part of the graph deals with two asymptotes simultaneously. You will never ever have a horizontal and a slant in the same function. You will have one or the other. You can have a horizontal only, you can have a vertical only, you can even have a slant only, but you will never have a horizontal together with a slant. And in our next video, we'll see why that happens. We're going to focus on the vertical one only for now. Next video, we'll deal with the other two. For this one, we'll just focus on the vertical. Find vertical asymptotes. And it's very simple. You can find where the function is undefined. Congratulations. You found all the vertical asymptotes. So knowing what value makes a function fail, knowing what value makes a rational function's denominator equal to 0, will give you the values of the vertical asymptotes. You have to be careful with notation, though. A vertical asymptote is a vertical line. Here is a vertical asymptote, potentially. Just saying 3 is not sufficient. 3 is a number. It's not a line. An asymptote is a line. So you must write it as the equation of a line. Just saying 3 or 7. No, it must be x equals. The equation of a vertical line is x equals some number. So when you're writing these, make sure you remember to do that. A couple of examples. Here's a function. Find all the vertical asymptotes. So, we don't care about the numerator. The numerator of a rational function should be defined everywhere. It's the denominator we have to deal with. So, let's find all the values that make the denominator 0. And since I know everybody can factor and solve quadratics at this point, you don't need me to go through the steps for that. We have -3, -4. That is not how we write vertical asymptotes, though. We need to write those as separate lines. So we have our two values. X equals -3, x equals -4. Those are the two values that give us our vertical asymptotes. So if we were to graph this, I don't entirely know what this function looks like, but I do know that at -4 and -3, we would have those two asymptotes. So our function would have to go, we'd have something between here, between these two, and then we'd have a component either doing this or doing this. We'd have the opposite over here. If I remember correctly, I think it kind of sort of looks like this, and then there's a piece that looks like this, and a piece that looks like this. I can't say for sure, though. But I believe this function looks something like that. That's all there is to it. Find the values that make the denominator equal to 0. One more. Find all the vertical asymptotes. Well, find where the denominator equals 0. Sometimes there's only one. And there it is. So if you were to graph this function at -1, we would have our vertical asymptote, and this function would probably look like something like this, I would think. And that's all there is to it. To find a vertical asymptote, you find the values that make the function undefined.